In our previous lecture, we began our discussion on the second fundamental theorem of calculus and discussed a little bit about why it was true from an algebraic perspective. In this video lecture, we're going to understand the second fundamental theorem of calculus from a slightly more geometric setting. So if we look at a graph of f of x, we said it's really the same graph if we graph f of x versus x or f of s versus s, right? So the difference is only the variable that you call the independent one. So it's only the variable of the x-axis, and when you perform a definite integral from a to b, it doesn't matter if you're integrating with respect to x or s, it's really takes the same, it's the same variable. So one person might describe this as a function of f of x, and his friend in a different lab or something like that might just call it f of s. But it's the same actual function, so when you do the definite integral, you get the same area under the curve. So for us, we're thinking of a function f of x that we're going to artificially change the name of the independent variable for the purpose of constructing an antiderivative. So let's draw just f of s. So suppose we have some function like this, f of s, and here's the point a. So we define this capital F of x as the integral from a to x of little f of s ds. So what that means is that x is the upper endpoint. So if I say that's x, and I integrate from a to x, I get the area under the curve between a and x. So it's this area right here. But x is a variable endpoint, which means I can slide x back and forth. So as I slide x out, let's say I extend x to over here. So let me make this, I guess, black. Extend it. Well, now it's the area from a to this value over here. So we get this whole area like that. So as I slide x, and x is continuous, you can think of it like a slide, it kind of sweeps out, and for any x value it says, okay, if I'm evaluating my function at this x value, it's the area under the curve from here to there. If I evaluate it a little bit later, we can even call this x1, x2, x3. So over at x3, well, capital F of x3 is going to be the area from a all the way up to x3. So the area kind of slides with your x value just like that. So we're going to use this kind of graphical interpretation to see another way of viewing why the fundamental theorem of calculus is true. Remember, last lecture we said, well, this would be capital G of x minus capital G of a if G is an antiderivative of little f, and so therefore capital F also has to be an antiderivative. Nothing wrong with that, but we're just going to take a slightly different and slightly more complicated approach today. So suppose I have a function capital F of x, which I define as the integral from a to x of little f of s ds. And my claim is that capital F of x is an antiderivative for little f, which means that if I take the derivative of capital F and I have capital F prime of x, I get little f of x. So let's prove it. So capital F prime of x is the limit as h goes to 0 of capital F of x plus h minus capital F of x divided by h. Old friends, right? So, okay, we're just going to use the definition for capital F of x in the limit definition of the derivative to compute capital F prime of x. Well, this is just the limit as h goes to 0 of 1 over h times the integral from a to x plus h f of s ds, and then minus the integral from a to x of f of s ds, right? So let's look at the graph. Here's s, here's a, here's f of s, and let's say this is the value x, and then we have x plus h like this. So we have the integral from a to x, like that. And then we have the integral from a to x plus h. So the integral from a to x plus h gives us this full area, and then the integral from a to x just gives us this first part of the area. So the difference is exactly the area between x and x plus h. So when I subtract these, I just get the integral from x to x plus h. And also that follows also from these rules of integrals. So if you integrate from a to b plus the integral from b to c is equal to the integral from a to c, or the integral from a to b, well, actually let's say the integral from b to c is just equal to the integral from a to c minus the integral from a to b. So if I subtract the integral from a to b from both sides, I get this one, and that's exactly what we have here. Integral from a to c minus the integral from a to b is just the integral from b to c. So what we can do now in simplifying this is to say it's equal to the limit h goes to 0, 1 over h times the integral from x to x plus h of little f of s ds. Now we know something about definite integrals because we have the definition of the definite integral, which also includes limits. But the big picture is that we're taking the limit as h goes to 0. So h is going to be really, really small. So let's assume that h is so small that we can do a good job of approximating this integral with a Riemann sum with how about one single subinterval? Because h is so ridiculously small, f is, well, you can always choose h to be small enough so that f is almost constant over between x and x plus h. Maybe h is 1 over a billion. Okay, well the integral from x to x plus h, f of s ds, is then approximately, well, let's use the left-hand Riemann sum with one subinterval. It's going to be f evaluated at the left endpoint, which is x, times the delta x. Now the interval width is with h, so it's going to be times h. So this is approximately f of x times h. And it gets closer and closer to being accurate as h goes to 0. So in the limit in particular, this one will equal this one because it becomes exact. So then this just becomes, so basically we get f of x times h over h, which just gives us f of x. Another way to see that same thing is to go back to the graph x plus h, here's a. So when we integrate and we're computing the difference of f of x plus h minus capital F of x over h, we're getting this area right here, which is approximately equal to the height, which is f of x, and then times the width, which is h, and then we're dividing it over h. So basically the derivative of capital F is just little f of x. So the rate at which you're adding to capital F of x is just equal to the height of the function at any moment in time.